salina. And they can form, as I said, either during or slightly before or slightly after the deposition of the sediments they are entrained in. And that's what diagenetic and syngenetic means. So if we have deposit formed syngenetically, it means that it formed at the same time of the deposition of the sediments by this percolation of hydrothermal fluids into a body of water, metal precipitation, mass flow deposits, and again another, and we've got this sequence of layered ores. Or else diagenetically, which is slightly after the precipitation of the sediments, or the deposition of the sediments the ore were deposited in, either through percolation in a soft sedimentary sequence, flowing of hydrothermal fluids through more porous horizons, or else by percolation onto the seafloor, and basically due to their greater density, these brines flow to the bottom and then percolate into the sedimentary substrate. So another type of deposits, not too unlike SEDEXs, is MVT, Mississippi Valley type deposits. These again are generated by hydrothermal fluids flow through sediments and sedimentary basins, large scale fluid flows. And they're often associated to orogenic events where the topography basically allows crustal fluid flow at a large scale. One difference from SEDEX deposits is that these are formed after the sediment lithification, so these are epigenetic, after the sediment has been made into a rock, basically. And they're mostly carbonate hosted, so we know more or less what caused the depositions, the reaction of relatively acidic fluids with carbonates, neutralization and precipitation. And they are called Mississippi Valley type deposits because they mostly occur in the Mississippi Valley, the Midwestern United States. 300 million years ago, basically we had two continents coming together, forming a chain, and there was an inland sea, a shallow inland sea at low latitude, perfect conditions for forming carbonate rocks. As we had continued collision and mountain building, basically all the fluids from this side of the range would flow down into this sedimentary basin that was full of carbonates, and so we had all these generation of these MVT type deposits, which are formed basically, as we mentioned, associated to carbonate horizons. So they're precipitated at relatively low to moderate temperatures from basin of brine. And they are, unlike SEDEXs, they are not, or not often stratified, but generally stratobound. So stratified means that they are horizontally kind of stratified together with the sedimentary units. Here we've got the sedimentary units, but the deposits not continues along the same unit, but kind of infiltrating a carbonate unit. But then we have certain carbonate units at certain horizons, so the deposits likely to infiltrate certain horizons and hence stratobound. One thing we need is basically the flow coming from the higher or the distal portion of the basin, and we need to kind of make it flow upwards, and that can occur basically through faults and brecciation. And for instance, if we have a basement high, the flow will be pushed upwards, and that causes depressurization and lower temperature. And we've got precipitation of pores within breccias. But as always, no single model fits all. So we can have either the reaction of acidic fluids with carbonate rocks, which increase the pH and cause pore formation, or else we can basically have mixing of oxide or oxidized fluids with reduced fluids, which are sulfide rich. That changes the redox state either through bacterial sulfate reduction or thermochemical reduction, and will lead then to the precipitation of all minerals. On to metamorphic gold mineralization. These are no direct magmatic inputs, although, as you know, the more you increase pressure and temperature and form metamorphism, at some stage you start melt, and so you might have some indirect influence of magmatic fluids as well. Fluids are mostly derived by dehydration of hydrous minerals during prograde metamorphism, and deposits form at about 250 to 400 degrees Celsius and a depth of 3 to 10 kilometers, but you can also get hotter and deeper deposits. The fluids are generally neutral to slightly acidic, and they are dominated by water and carbon dioxide. As you can see here, this is where we are expecting to see orogenic type gold, or else in mountain building environments, such as here. So again, we need a way to generate fluid pathways. So we have crustal scale shear zone, because as I said, we need a lot of fluid to flow through the system to precipitate enough gold. And so if you just have local fractures and faults, they can't basically allow enough fluid to form viable deposits. Whereas if we've got crustal scale shear zones and fracture zones and fault zones, a lot of fluids from many portions of the crust can basically be entrained and allow precipitation. And overdeposition in these settings occur either by phase separation or fluid rock reaction. So for instance, flood phase separation, as I was saying, where we got fault zone, movement, we generate spaces, and so we form these veins and dilation of faults that are filled with fluids, precipitate pores, and gold, and these are usually associated with free gold, as opposed to the system where we have a reaction with a whole rock, where gold is transported as a bisulfide complex, and reaction as it consumes the H2S. Sorry, this is the it reacts the H2S with iron oxide, for instance, to form pyrite that causes dissociation of the gold bisulfide, and so we've got basically precipitation of gold within the sulfides, so gold hosted in the pyrite, arsenic pyrite, marcasite. And this is what some of these fractures look like. So this is particularly small, about 20 centimeters across, where we've got a proximal zone proximal to the vein, where we've got these pyrite precipitation and gold relatively concentrated. As we move away from the zone, we go from a white mica, chloride dominated alteration assemblages to a chlorite, and then later epidote, and as you can see, basically the gold disappears, or not disappears, but never introduced to the system. The previous image was for a mafic host country rock. This is for a felsic host country rock, where we basically have the vein that contains pyrite and gold. And further away again, we've got the alteration halo with gold abundances decreasing. And orogenic gold is being mined in New Zealand, for instance, at Riften or Macrae's. And if you're interested, you can go and look at this website. I know I shouldn't be advertising for enemy university, but they've got some smart people that look at gold in Otago. And as you can see, you can read through that and the history. We've got both gold that occurs as native, associated with minor sulfides, so these occur by phase separation, or we've got this fluid drop reaction with gold within sulfides. Carlin-type gold mineralization is kind of related, but rather than occurring in a compressive orogenic environment, it occurs in extensional settings. So again, large crustal scale faults allow fluid flowing, and we have reaction, for instance, carbonate rocks form in iron sulfides and gold hosted within iron sulfides is either gold glass, arsenic or pyrite. And just like to point this out, on Friday there's going to be a seminar 4 to 5:30 by this lady who's probably more experienced than I am on the Carlin-type gold deposits, as well as other gold deposits, porphyry, copper, and volcanic hosted gold. So if you're interested, please come along. IOCG deposit is the last for the day. Stands for iron oxide copper gold, and it's not entirely well defined, so there is a complete spectrum of types, and often they come along and they name the type on the location, so it seems like every location has got its own type and different characteristics of each. Last, the magma type, magmatic associations, whereas these occur in a park setting. Alkaline magmas is a more intraplate with alkalic and carbonatitic type magmas. But the thread that basically links all of them is this circulation of meteoric fluids and interaction with hotter, deeper magmatic fluids that causes precipitation of metals. But they are interesting because of the very large scale of mineralization that are usually associated with. And this is a bit of a spider web, but if you can find your way through this, you'll sail through the rest of your life. Basically, we can have different inputs of different water, fluid type, magmatic, metamorphic, connate, meteoric, groundwater, and the solutions then, depending on where they're flowing through and what causes the reaction or the precipitation of the metal, will form different deposit types. And as I said many times, now there is no black and white in nature. So you go from one side to the other, just basically by changing small parameters. So we looked at today the origin of fluids and the processes that cause basically all precipitation, whether mixing, boiling, or reaction with the host rock. That leads then to all these different deposit types depending on the setting and what causes the precipitation mechanism. And next lecture on Monday, we'll be looking at all deposits related to supergene or sedimentary environments, such as banded iron formations, not to be confused with ultimate, and supergene origin and primary gold. Wow, that was real
Clearly, they was hydrothermal.